Hello everyone, welcome back to this online class. Today we are going to look at the method of Fourier transform as used in solving partial differential equations of the second order. In particular, we are asked to solve the one-dimensional heat conduction equation given by partial u with respect to t is equals to k times second partial derivative of u with respect to x twice. The boundary conditions vanish, or simply the solution vanish, u of xt approaches 0 at the end, that is when x approaches plus or minus infinity. Also, the derivative of u with respect to x approaches 0 as x approaches plus or minus infinity. That is for all time t greater than 0. And the initial condition, that is when time is 0, our solution should be f of x in the domain that extends from negative infinity to positive infinity. The f is an arbitrary function. So how do we go about this problem? Using what we call the complex Fourier transform method. Remember, we have three types of Fourier transform. The complex one, which applies for the complete domain from negative infinity to the positive infinity. We'll also look at the Fourier cosine transform and the Fourier sine transform. Those ones are for half-range domain. So, even before we look at how to go about it, first of all, you need to say let f be the Fourier transform operator. So we'll operate with the f. Look at our PDE. The K in the PDE is thermal diffusivity. Thermal diffusivity. Now, what you do is to operate with f on both sides of the given equation. So the first step, step 1, you're going to operate with f on both sides of the PDE. So what are we going to get? You write Fourier transform of partial u partial t is equals to Fourier transform of k is a constant, times second partial derivative of u with respect to x twice. Remember, this Fourier transform is in the variable x. So we are saying let f be the Fourier transform operator in the x variable. In the x variable. Why are we saying in the x variable? Fourier transform is simply should operate, that operator should operate on that variable which extends from negative infinity to positive infinity, the complete interval. So when you have a variable that starts from 0 to positive infinity, you cannot operate on that variable. Only operate on variables which extend from negative infinity to positive infinity. And so we are going to operate on the variable x. So when you operate on the variable x, you assume that the t variable here is a constant with respect to the operator f. Now, you see, k is a constant, and this can now be factored out because of the linearity property of f. So k constant, then a Fourier transform of second derivative of u with respect to x twice. what have I used here is the linearity property of the F operator. So, because we are saying we are treating the variable t as a constant and only operating on the variable x, our transform of the derivative with respect to t will be this one. So it will be now ODE, DDF, DT, I mean, DDT of the Fourier transform of U. Remember, U is a function of xt. Fourier transform of U of xt. That's what you get when you transform that derivative. Is equals to k is a constant. When you transform derivative with respect to x, you need to get, of course, you know that in general, the Fourier transform of the nth derivative of u with respect to x raised to n, this should always give you iota times omega raised to n times the Fourier transform of u. That's what you need to get in general. So when you have second derivative, we will now talk of iota times omega raised to 2, because our n is 2, times the Fourier transform of u of xt. That's what you get. And remember, what you're calling iota is the square root of -1. So this means that I squared will be equal to -1. So that on the right hand side, we can now get this as negative k omega squared. Why negative? Because of the I squared. Then times the Fourier transform of u of x t. That's what we have. I can take everything to the left hand side so that I have an equation that I can solve easily. So you can write or d dt of the Fourier transform of u of xt, then plus k omega squared Fourier transform of u of xt. This should be able to give us 0 on the right hand side. This one here is an ODE. This is an ODE of the first order with the constant coefficients. Of course, it is separable. You could also solve as a linear ODE, or you can solve using the D operator. This is a linear ODE, or simply an ODE of first order with the constant coefficients. There are three methods of solving it. You could use D operator, you could use the integrating factor method, or you could solve this as a separable ODE. We are still going to get the same answer. So I want to use D operator. So let D capital be derivative with respect to t. So if that is the case, then our equation will now be d plus k omega squared operating on the Fourier transform of u of xt should give us 0. Of course, you should also take note that it is a homogeneous ODE because the right hand side is 0. So what is the auxiliary equation? Let me talk of auxiliary equation. You need to equate the coefficient of that Fourier transform to 0. So d plus k omega squared is equals to 0. So what about the roots? It's just one root. When you make d the subject, you're going to get negative k omega squared. And this is a real root. Real root. When you have just one real root, how should you write your general solution? So you can say that therefore, we know that now the Fourier transform of u of xt should now be equal to a constant, call it c or even c1, exponential negative k omega squared t, where c1 is an arbitrary constant, which we need to determine. Remember, somebody might be asking, what do we do with the boundary conditions? Those boundary conditions are what gave us this formula. When you apply those boundary conditions, you get this formula that we have used in our equation. So already these boundary conditions have been taken care of. What you need to apply is the initial condition. So you don't need to derive this because already this was derived in the previous lecture. So you only need to apply this formula. And to get this formula, it is derived from the boundary conditions. So I hope that point is taken. So now we need to apply the initial condition so that we see whether we are going to get the arbitrary constant C1. So that will be step 2. Step 1, we have solved it. And now we have our solution in terms of the transform. So step 2, you write apply the initial condition. What are we told? That u of x0 is equals to a function of x. That's an arbitrary function. So you also need to take the transform on both sides. So therefore, this means that the Fourier transform of u of x0 should be equal to the Fourier transform of f of x. Let's call this u capital a function of omega. So that means in this equation, this solution that we have found, I need to substitute t is equals to 0 so that our transform will be equal to u of omega. So when I put t is equals to 0 and the Fourier transform be equal to u of omega. In this equation, the one that I have ticked, so what are we going to get? It will be u of omega is equals to C1 times exponential. Because time is 0, this will be exponential 0. So this simply means that your C1 is equals to u capital of omega. So therefore, if we replace it back to that solution, this one, we get Fourier transform of u of xt is equals to the capital U of omega times exponential negative k omega squared t. That's the second step. We have applied the initial condition to get that. Then the next thing was, let me bracket this one. The last step, step 3, you now operate with F inverse. That is the inverse Fourier transform on both sides. On both sides of this equation, the one I have ticked. Now, when you operate with F inverse on the left-hand side, you are going to get U of xt. Remember, F and F inverse are inverses of each other. So F inverse of F is an identity operator. So we remain with the U of xt is equals to F inverse of U capital, a function of omega, times exponential negative k omega squared t. Now the task is, how do you find the inverse transform of that function? That is the question. So this is, look at our definition of the inverse Fourier transform. I am going to use convolution theorem. Why? Because these are a function of omega. Again, this one is a function of omega. Let this one be G, a function of omega and T. So because we have a product of two functions of omega, we use convolution theorem. So use convolution theorem since we have a product of two functions of omega. That is when you're getting the inverse transform. So, you remember the convolution theorem? Let me state it. Convolution theorem. That I can use another color. That F inverse of, let's talk of, let me look for a better function to use. F inverse of U of omega times G of omega T is the same as the integral from negative infinity to positive infinity of F of S times G of X minus S T ds. That is the convolution theorem. Convolution theorem. Now, what is F of S and what is G? You can say where F of X is the inverse, F inverse of U of omega, and G of xt is F inverse of G of omega t. So if you know F and G, the small one, then it is easy to get the inverse of a product of two functions of omega. This is called convolution theorem. So this is a special theorem that you're going to use. Let me bracket it that way. So therefore, we expect that this can now be written as the integral from negative infinity to positive infinity of f of s times g of x minus s t ds. So what do we need to find? Already we don't know f of x. It was an arbitrary. So we only need to know or to find g of xt. Because once you know it, it is easy to find g of x minus s times t. So I'll call this equation star. I'll call this equation star. Now let's find the function, the small g, as a function of x and t. Of course, we know that f can just write where and use another color, where f of x is equals to f inverse of u of omega. And g of xt is equals to f inverse of the other function. Look at this one, exponential negative k omega squared t. Another thing you need to take note of, also take note, another color, that when we talk of the inverse Fourier transform, f inverse of a function of omega, let's say f inverse of g of omega t is defined by 1 over 2 pi the integral from negative infinity to positive infinity of that function g of omega t times exponential. Let me take this to the left so that I can write here exponential I omega x d omega. That is how to find the inverse transform, the inverse Fourier transform of any given function of omega. This formula is very important. Very, very important. This is what you're going to use to find the inverse of exponential negative I negative k omega squared t. So I've talked of the convolution theorem. We have also talked of how to find the inverse Fourier transform. So how will this look like? It is now equal to 1 over 2 pi, the integral from negative infinity to positive infinity of exponential negative k omega squared t times exponential I omega x. This is the omega. And this you can as well write as 1 over 2 pi, the integral from negative infinity to positive infinity of exponential negative kt omega squared plus ix omega d omega. Now, how do you integrate it? That's the question. Look at our exponent. It's a quadratic expression. Our exponent, this one here, is quadratic. This one is quadratic. So what do we use? You complete the square. Complete the square. We are going to complete the square in that exponent because it is quadratic. So let me complete the square this side. Remember that negative kt omega squared plus iota x omega can be written as, let me use another color, can be written as, blue is okay, negative kt bracket omega squared minus iota x over kt times omega. I have factored out the negative kt. Why? Because you see, when you're completing the square, you must ensure that the coefficient of the highest power of omega in this case should be equal to 1. So then you complete the square inside the bracket. So this is the same as negative kt omega squared minus iota x over kt omega. I need to add a number c plus a number c, then minus the same number c. And how do we get the number c? It is always equals to b over 2 squared. B over 2 squared. What is our b? Our b is the coefficient of omega. So this is our b. The one I'm circling is our b. So this is b. The whole of that, so I should point at the circle. Just point at the circle. And the whole of this gives us b. So it is now b over 2 squared. So what is, let me extend this. So we'll talk of now, b over 2 squared will now be equal to negative ix over 2kt. And this is supposed to be squared, which is the same as negative I squared x squared over 4k squared t squared. That's what we have. And which you can simplify to get, remember I squared is negative 1, so this will simply give us x squared over 4k squared t squared. That's what we get. So back to this completing the square, so that here we will now write it is equals to negative kt. We have omega squared minus ix over kt omega. So we are adding x squared over 4, that should be 4, x squared over 4 k squared t squared. That's the c that we're adding. We also subtract the same c, x squared over 4 k squared t squared. You subtract and you also add the same number. So I'm going to group this to form the first bracket. Look at the first bracket. When you factorize, what do you get? That is now a perfect square. So that will give us negative kt. When you factorize the first bracket, you're going to get omega minus ix, omega minus ix over 2kt. And this is supposed to be squared. Then minus x squared over 4k squared t squared. That's what we get. If I take this one inside, the all of this negative kt, how can it be written? So this can as well be written as, if I open the bracket, I'll get negative kt times omega minus iota x over 2kt. This is supposed to be squared, then plus kt x squared over 4k squared t squared. And now we can simplify. We can now simplify this so that we are going to get this is equals to negative. Remember, kt is the same as the square root of kt, and this is squared. It's the same thing, times omega minus iota x over 2kt, this is again squared, plus, you see the kt will cancel with these powers so that we have x squared over 4kt. That's what we have. So now you can now take this, the root kt inside, because you see both of them are squares, so it just times root kt. So that this can as well be written as negative of the square root of kt times omega minus iota x times root kt over 2kt. This is squared plus x squared over 4kt. So that's what we have. When we complete the square, we get that. Then now we go back here and replace it. So that in our integral, we are going to write this. It is now equal to 1 over 2 pi, the integral from negative infinity to positive infinity of now exponential. What did we find? We got negative the square root of kt omega minus iota x root kt over, that was, let me check, 2kt over 2kt. This is squared. Then I can see this plus x squared over 4kt. And it is supposed to be integrating with respect to omega. That's what we got when we complete the square. So How else can you write this? This can as well be written as 1 over 2 pi, the integral of from negative infinity to positive infinity, exponential negative, the square root of kt times omega minus iota x times root kt over 2kt is squared times another exponential x squared, that should be x, exponential x squared over 4kt the omega. Now, anything that does not depend on omega can be factored out. Anything which does not depend on omega can be factored out. And so what are we going to get when we factor out the exponential x squared over 4kt? Let's see. There's some sign that we have missed. Let's just go back to our completing the square. We were adding c and subtracting c. So here it was negative. Then the negative kt will multiply so that we have positive kt. And then we missed out something somewhere. Let's just check. Look at the completing square. We added, and what were we adding? The value of c. We also subtract the same value of c. And so remember, I squared is -1. So we'll expect to have kt. And so that should be a positive instead of a negative. Just a minute. So there's a slight correction here. Look at where we were squaring. It was negative I squared. Of course, even the -1 we did not square. This negative must also be squared. Everything was squared. So that here we need to get negative x squared. So just change it. Negative of x squared. That's our c. Our c that we are adding should be negative. So even the sign here must change. We are adding the negative, not the positive. So these signs must change. This is, we are adding c, then subtract negative. Negative becomes positive. Then I expect here to be positive, so that again here it will now be negative because now you are taking the negative kt inside. So this should be negative, just a change of sign. A change of sign. This should be negative. Even here it's supposed to be negative. We are just tracking the sign that we left. So even here is supposed to be negative. And also here is negative. So that correction is vital, very important. Where did it start from? Because you see here we were squaring. A negative squared becomes positive. It is this one that confused us. And also the I squared is negative. So that's why we still have the negative because of the I squared. But -1 squared is positive. So take note of that. And so now we have completed the square. Let's come back to our problem. We are just tracking the signs here. We expect this to be negative and also a negative here. So this should be minus and another minus here. So that's now okay. We have corrected it. Now, I told you that anything that does not depend on omega, I mean, you factor it out. So you see this exponential. I can't see an omega inside here. So we can as well factor out this. Let's take it here. So that this integral can now be written as 1 over 2 omega, 2 pi, I mean, correction, 1 over 2 pi times exponential negative x squared over 4 kt. Now the integral from negative infinity to positive infinity, exponential negative the square root of kt omega minus ix root kt over 2 kt. And this is supposed to be squared the omega. Now we are going to use a substitution. I cannot use u because already we have u as our dependent variable. Let me use z. Let z be equal to the whole of this in bracket, that is root kt times omega minus iota x root kt divided by 2 kt. Let that be z. So from here, you can just say therefore dz d omega. Because we are moving now from omega to z, that is simply the square root of kt. You can as well say that d omega, when you make it the subject, it will be equal to dz over the square root of kt. So back to our integral. This integral can now be written as 1 over 2 pi exponential negative x squared over 4 kt times the integral. What about the limits? Limits, when z, these are omega, limits for omega. Now, what are the new limits for z? When omega is negative infinity, what will be z? It will also be negative infinity. And when omega is positive infinity here, you will find z is equals to positive infinity. So this will be exponential negative z squared times dz over root kt. That is omega, d omega. D omega is the same as dz over root kt. The square root of kt is independent of z, and so we can factor that out. So that this can as well be written as 1 over 2 pi times, I can see this, the square root of kt, then times exponential negative x squared over 4 kt. Then the integral from z is equals to negative infinity to positive infinity exponential negative z squared dz. Now, from the properties of error function or from the gamma and beta functions, the square root of exponential negative z squared dz from negative infinity to positive infinity is always equals to the square root of pi. I said the integral of exponential negative z squared dz from negative infinity to positive infinity should give us root pi. So therefore, this can now be written as the square root of pi over 2 pi times the square root of kt times exponential negative x squared over 4kt. And you see, I can see there's pi in the numerator, another pi in the denominator. I can combine them. Look at, we have pi raised to 1 over 2 divided by pi. So it's the same as, this is the same as pi raised to negative 1 over 2, which is the same as 1 over root pi. That's what we have. So that this can now be written as 1 over 2, the square root of, now even there's root pi and also there's root kt. So I'll just combine them under one square root. So that would be pi times kt exponential negative x squared over 4kt. So that's what we have. Now, this is our, you can just say, therefore, g of xt. G of x is equals to this. So hence, we need to find g of x minus s t. So where there is x, you put x minus s. So what will this be? It will be 1 over 2 the square root of pi kt exponential negative. Now we are replacing x by x minus s. So this will be x minus s squared over 4kt. That's what we have. And now our particular solution, we now replace what you have found. Look at where we started. The whole of this was just to find g of xt. As I have explained, I was very slow so that we understand each and every concept. So we'll come back here to our equation star. So what will be equation star? How will it look like? That will be our particular solution. So therefore, our equation star will now become equation star. Now we are going to substitute this into equation star. So let me just write here equation star. Look at our equation. On the left, we had u of xt. What about the right-hand side? It is the integral from negative infinity to positive infinity of f of s. F was arbitrary, so I don't know f of s because it's an arbitrary function. Then times this other one, g of x minus s times t. So times 1 over 2 root pi kt. So root pi kt times exponential negative x minus s. This is supposed to be squared, everything over 4kt ds. That's what you got. You know, anything that does not depend on s will be factored out. So this one is a constant. Take it outside. It is a constant, so we are going to take it outside, let it be here. So that this you can write as or u of xt is equals to 1 over 2 root 1 over 2 root pi kt. That's outside. Then the integral from negative infinity to positive infinity, f of s times exponential negative x minus s is supposed to be squared, everything over 4 kt ds. This is our solution. If you knew the function f of s, then you can be able to find the particular solution corresponding to that given function. But in this case, we are not given the function f of s, so we leave our solution as this one. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to like, share, and comment this video. When we meet next time, we look at other problems in Fourier transform. Bye-bye.